Okay, so we're given the positions of a bishop, a white bishop, and a black pawn on a standard chessboard, and we basically want to know, can the bishop take the pawn? Is the bishop threatening the pawn? And if you're unfamiliar with the rules of chess, basically a bishop can only move diagonal, which is kind of interesting because that means a bishop can only move on one color of square. You know, like this bishop will only travel on dark squares for its entire existence. It would never be able to make it onto a light square. So it's kind of tragic, but you know, such is the life of a bishop. Okay, so in this example, yes, the bishop can take the pawn, so we would return true. In this example over here, the bishop cannot take the pawn, and so we'd say false. And then you might say, well, couldn't the bishop take the pawn? You know, what if it did something like this on one move and then did something like this on the next move? Well, ignoring the fact that the pawn would take the bishop if it tried to do something like that, it also specifies in the problem in one move. It has to be in one move. So it has to be currently threatening the pawn. So that's important. Okay. So I guess at this point, I think we probably have an idea of what the problem is asking, and we know at least some of the challenges we're going to be encountering here. So first of all, get coordinates. That's a function we want to be writing, and we're going to start with a position, right? So algebraic notation, chess notation. I'm just going to call it chess notation. I think that makes more sense to me. Anyway, so it's in chess notation. You know, we're given, like, for example, this would be D4. D4 would be the coordinates of this bishop here because the D over here and the 4 over here. Okay, but instead of D4, we would want like 0, 1, 2, 3, and 0, 1, 2. Yeah, okay, so 3, 3. That's what we would want. So basically, let's do that. So if we're given, all right, here's what we want to do. Let's pull out a nice color for this one. I'm thinking like kind of a pale orange or something like that. Yeah, good. So we want this to be 0. We want that to be 1. We want this to be 2, 3, 4, 5, etc. And then, you know, it probably seems like this is going to be the tricky one because we're converting letters into numbers, but keep in mind this one is non-trivial as well because we don't want these to be exactly the same thing. Like we want them to be basically the one less than what it is. Okay, cool. And the other thing we need to keep in mind is since we're given this notation in the form of a string, like this right here would be like quote unquote D4. So that's the string D4, which means that this right here is not the number 4, it's the string 4. So we'll have to convert it into a number and then subtract 1 in order to get our, I guess I'll call this the Y position. I'll call these the X's down here and these the Y's over here. And I realize that's not really, well, actually, okay, so this is actually kind of consistent with Cartesian plane sort of notation. So great, X and Y, awesome. So let's implement this. So basically, for the X, we're going to get the character code of the first character in the string. So we're going to do, you know, like position.character code at 0. And then we're going to subtract from that the character code of capital A. And then we already talked about how we're going to get Y. So let's go ahead and do that. So we'll say constant X, because we're not going to reassign this thing. It's going to be constant. Constant X is going to be position.character code at, and we're going to do 0 because we want the character code of the character that's at position 0 or at index 0 of this pause string. Okay, and then we're going to subtract from that A dot character code at. And that's a capital A. And I didn't mean to put the lowercase L in there. Sorry about that. Okay, cool. So that's kind of nice. This, you know, we could get the actual value of that. We could go and look at our ASCII table and say, oh, it's 65. Let's just subtract 65 from it. And, you know, forget about all this over here and just do minus 65. We could do that, you know, if you wanted to. We could also just do something like this and put it up here and say, like, constant A is assigned the value of all that stuff. And then just put A over there. Pardon me. All right, sorry about that. Something in my throat. Okay, so, so basically this right here should give us the x coordinate. It should convert this capital letter into a number between 0 and 7 inclusively. Okay, and then we'll say y is going to be parse int, because we want the integer version of position at 1. Yeah. And then we want to take away 1 from that, so that it's also 0 based, just like its partner, the x values, right? Because the x values are going to go 0, 1, 2, 3, as opposed to these, which are like 1, 2, 3, 4. So we want y to do the same. That's why we're doing the -1 at the end. And then we're just going to say return x, y. Something like that. Okay, cool. And while we're here, we might as well do the reverse as well. So we'll do get position from chords. And we'll just assume that chords is going to be an array. It's going to be like the x and y that we have over here. And we want to convert it into our chess notation over here. So we'll say, I guess, okay, so for the like A, B, C part of it, we'll do like a string dot from character code. And it's going to be A plus chords at 0. Yeah. Okay. So chords at 0, that's like the x value over here, right? So we're taking the x value, and let's say the x value was 2. Okay. So we should expect capital C from that. So we say, okay, we want the a string that comes from the character code, which is equal to, I guess, the 65 that we get from this, plus whatever x value you're giving me. In this case, the x value was 2. So we'll do 65 plus 2. Oh, what was that on the ASCII table again? 67? Oh, it's capital C. Exactly what we're looking for. Great. Okay, so there's that, but then also we want to add to that plus the y value, which is chords at 1, plus 1. And we already know the y value here will be an integer. It'll be a whole number, but importantly, it'll be a number. So that means this thing over here is considered addition, not concatenation. Really, really important to keep those two separate to make sure we have a good sense of the difference. So, okay, in this case, we're adding the 1 to the y value, and then in this case, we're concatenating, because this thing over here, like this stuff, well, that's a string. This stuff inside the parentheses, that's not a string, but if we wanted to be explicit about it, we could do, like a string or something like that. It's not going to make a difference. We don't need to put the toString there. It's going to understand. I guess there's no harm in putting it though, so might as well. Okay. Sorry, I thought I was about to sneeze there. Okay, let's keep going. So, all right, we've got get position, we've got get chords. Let's test it, I guess. We'll just do like a quick return, and what do we want to start with? Get chords of this thing, D4, let's say, D4. And we're expecting what, 3, 3? Yeah, 3, 3. Let's do H, 1. Okay, and we should get like a 7, 0. Yeah, 7, 0. Okay, cool. And maybe let's try something like a get position of 2, 7. No, we already did a 7. 2, 5. That's better. So 2, 5. That should be C. Oh, whoa. C6 is what we want, but we're getting null. Why? Because this doesn't say return. Okay, there we go. That makes sense. Yeah, C6. Great. That's what we were looking for, I think. Yeah, that's what we were looking for. Cool. So that's good. And I guess I'll just move that over for a little extra room. Great. So we've got our working functions here, get chords, get position, and we should be able to really use them sort of in tandem with each other, right? So if I were to do like a get chords of get position of 2, 5, I should probably get 2, 5, right? Like as though nothing ever changed, because I converted it from coordinates to chess notation back into coordinates. Okay, great. But now I'm noticing a problem. Look at this. This was deceptive. On the board here, these are capitals. Over here, not capitals. They're giving us these lowercase codes. So I'm going to have to update this a little bit. I'm going to say that this is going to be lowercase a, and this is going to be lowercase a, which means I got to update all these guys. Too bad, but that's fine. Yeah, I think we'll be fine. I think everyone's going to be fine here. So here, let's get rid of that. We'll see if this is still working good. And it is. Okay, so that's what we're looking for. Awesome. All right, so we've got those two functions. They're working. Those are kind of like, think of it this way, right? We sort of have like our Rosetta Stone here. You know, we know how to translate between the language of chess and this more sort of mathematical language that we understand and can work with within our function. So probably what we're going to do for our algorithm is we're going to take in these like chess codes, we're going to convert them to coordinates, we're going to do some work with those coordinates, we're going to do some calculations, change them up, and then we're going to have some kind of answer. Maybe we'll have to convert it back into chess notation or something like that, but we'll see. So what's our plan here? Well, I'm thinking we should start by just making a list of all the codes, like all the chess notation codes for all the spots that the bishop is threatening right now. So let's get a nice cool blue color. There we go. And we'll put the codes in here, at least for some of them. So like, for example, this one over here, well, that's E5. Still getting used to this new mouse. Sorry about that. This one here is F6. This one down here, oh, that's E3. And I don't know, this one here, that's B2. Whoa. Okay, those are getting pretty bad. I'm not going to fill in every one of these, but the main thing is I'm just going to like keep a list. I'm going to have an array that just has all these codes in it. And then I'm just going to say, is pawn, like is this thing right here, is the chess notation code for pawn's position, is it one of them? Is it in that array? Because if it is, true. Yeah, it's in one of the threatened spots, so we should return true in that case. If it's not, well, no, it's not being threatened, so don't worry about it. Okay, cool. So that's what we're gonna do. So let's say let threatened be assigned the value of this empty array. Threatened as in, you know, what spots are, what tiles, what position are within striking range for the bishop. I guess I could have called it like within range or something like that. But threatened, yeah, I think that's kind of a chess-like term, right? I don't know. Okay, so we could call it something longer too, you know, like spots the bishop is threatening or something like that. But we don't want to be too verbose about it. We want to keep it pretty terse as much as possible. So, okay, we'll roll with this for now. Okay, so what are we going to have here? Well, first of all, I guess we could start by putting the square itself, like bishop. We could just put that in here, but I don't think we will. And the reason I say that is because we're not that interested in whether or not the bishop is threatening its own square. Like, they're not going to overlap anyway. Like, what I'm trying to say is it's not going to be like the pawn is on top of the bishop. You know, they're not going to be on the same square, so we don't actually need to really worry about that. Okay, so what are we going to do? What are we going to worry about? So let's do something like this, okay? Let's start with this. So we'll say for what are we even gonna do here? Okay, I think I've got an idea. So yeah, okay, so for let steps be assigned the value of 1, and we'll think about what our repeating condition is going to be in just a sec, but then we'll do steps plus plus after that. And here's what we're going to do. So, okay. So here's how we'll do it. We'll say let temp x be assigned the value of, oh, and I guess I should do this. So let's say let x and y be assigned the value of get coordinates of bishop. Okay, cool. So x and y now are just going to be the starting position of the bishop. Great. So temp x is going to be x plus steps. Let temp y be assigned the value of y plus steps. Because they both need to move, right? I mean, it's not like we're just going in the x direction or just going in the y direction. It has to be both x and y changing by the same value each time. So, steps. Okay, cool. So we've got temp x and temp y. And then we'll say, well, if, and this is going to be a big if, because we need to say temp x is within range. And temp x is less than or equal to 7, I think, right? And same needs to be true for temp y. So, like, you know, there's a lot to be said for this one. Temp y is less than or equal to 7. Not 67. Okay, there we go. So, if all that's true, if this, you know, next set of coordinates here is within range, then we're going to say, oh, threatened dot push get position of temp x and temp y. And you know what? I'm realizing now, maybe I shouldn't have used an array as the input here, because it feels a bit silly that I'm like putting these into an array and then just, yeah, actually, you know what? Yeah, I think I'd like it better if we could just do it like this. So instead of chords at 0, I'll just say x, and instead of chords at 1, I'll just say y. And I do have to say I feel a lot better about that. And now we don't have to do this stuff, which is good. This is great. This feels great. Okay, there we go. And then at the end here, let's just return threatened. Let's just see which tiles we're actually collecting here, what we're actually picking up. Okay. I understand why that happened, because I didn't tell this loop to stop under any circumstances. So I'm going to put an else in here, and I'm basically going to say, well, if temp x or temp y get to a point where either of them are out of range, then stop this madness right away. We want to break. Get right out of that loop. Don't let it execute another time, because it's just going to get way out there. So yeah, that's important because we don't have that. Okay, so this is H1, so I get why there's nothing inside the array. Ah, there we go. Okay, so we got a bunch of stuff here. So this is where the bishop starts at A1, so it starts right here. And then we get B2, cool, C3, D4, E5, F6. So this is great. I mean, these are giving us the right spots. Is it giving us all the spots? Let's find out. So this one over here, this is where bishop starts at A5. Okay, so if we're starting at A5, then yeah, we'd get B6, we'd get C7, we'd get D8. But what about B4? What about C3? What about D2? And what about E1? We're not getting those. The reason is because we're only going out in one direction here. We're only going upright, you know, because we're doing plus steps. So the way we're going to do this is going to be a little, maybe a little bit complicated, but it's nothing we can't handle. So here, we're going to say constant direction. Yeah, direction. And it's going to be, we'll start with 1, 1, okay? And for this, we'll do, actually, instead of direction, let's just call that D. D for direction. Okay. So we'll say D at 0 times steps, and this one will be D at 1 times steps. Okay, so what's this all about? Right now this is making absolutely no difference. So you might think, it's kind of stupid, you know? Like this one, we're still just getting B6, we're still just getting C7, D8. What we want is something more like this. So now I'm changing the direction. I'm saying, yes, it's going to increase in the X direction, but it's going to decrease in the Y direction, which is why we're getting B4, C3, D2, and E1. The thing is, we don't want just one of those. We don't want just this one set or just that other one set. We want all the possible directions. So I'm going to say constant directions. Yeah, there's a lot to take in here, but we'll get it all. So directions is going to be an array of arrays. It's going to start with 1, 1. Next one is going to be 1, negative 1. Then negative 1, 1. And, or actually, just to make it sort of like looping around, let's make them both negative there. Okay, great. So those are directions. And we'll say let direction index be assigned the value of, actually, no, I don't think we need that. I don't think we need that. Because here's what we're going to do. We're going to do a larger loop around this. We're going to say for let D of directions. Yeah. And that's just going to go through every one of those directions in our array here. So this will be D, and then this will be D, and then that will be D. And before I do anything else, I should probably paste that in. And it should be indented like that. Okay, so let's try it. Okay, so still getting nothing for test 2 there. And we'll look into why that is. Oh, okay, we're getting nothing for test 1 now. We're getting lots of stuff for test 3. Why are we getting nothing from test 1? It's A1. Oh, silly me. I forgot to delete this part where we're actually assigning the value of D. D is just going to be whatever this is. So yeah, if I'm reassigning it, then I can see how that'd be an issue. Okay, cool. So now we're getting the ones we're looking for. So this is one where we start at H1. And so we should expect, yeah, G2, F3, E4, etc. Okay, so this is getting the tiles we're looking for, I think. We're going in all directions here, which is good. Now, what I would have done in the past is something like have a direction index, which loops through these, but we don't really need to do that. Yeah, that would be overkill for this one, so we won't worry about that. Okay, before we go any further, I mean, let me know if you have any questions about anything that's going on here. So we've talked about like the get coords, get position, these two functions here. This is just sort of for converting between different ways of expressing the coordinates here. This is just a constant we're using. Don't worry too much about that. It's just, what was it, 97? I think it's 97. Yeah, 97. So let's think of that as just the number 97. But this stuff down here, this is the stuff I really want to make sure is making sense. So threaten, first of all, is the array of tiles, of like chess notation codes for all the tiles that the bishop is currently threatening. So if the bishop is standing here, then they're threatening this. So I don't know if there is one where the bishop is standing at D4. I guess, you know, we could do that. We could just say like bishop is assigned the value of D4, and we'll see what tiles we get. So it should be like E5, F6, G7, H8, and then it should move on to E3, F2, G1, which I can see are in there. And then after G1, it should be going after this one. So C3, B2, and A1. Finally, C5, B6, and A7. That's exactly what we're getting here. So why are we getting that? Well, basically, okay, so let's get rid of that. So we're starting out with having no tiles in our threatened array. Then when we do this, we're getting the position of the bishop just as like an array of X and Y values, so it's easier to work with. Then we're getting these direction things, or we're stating these directions. And what is it? Like 1, 1, 1, negative 1. 1, 1 would be going right 1, up 1, right 1, up 1, right 1, up 1. 1, negative 1 would be right 1, down 1, right 1, down 1, negative 1, negative 1, left 1, down 1, left 1, down 1, etc. And then finally left 1, up 1. The point is, these are the 4 directions we want to be moving in to sort of find all these tiles here. Okay, so basically, we say we have this outer loop, which is saying, okay, first do all of this stuff where D is 1, 1. Then do all of that stuff again where D is 1, negative 1. So basically for each direction, we're repeating this entire for loop. So what is this loop doing? Well, it's basically telling us how many steps we can take in that direction. Or it's not so much that it's telling us how many steps we can take, it's just for every one of those steps, we're going to push the chess notation code for that tile into the threatened array. So temp X and temp Y, those are going to be the coordinates of our new position. So if we're starting here at 3, 3, then we'd have 4, 4, 5, 5, 6, 6, 7, 7, and eventually 8, 8. But when it gets to 8, 8, we're checking this and we're saying, oh, well, temp X and temp Y are actually outside of the range here. So they're not less than or equal to 7. It doesn't have to be both of them, even if it was just like, 4, 8 or something like that, or like 2, negative 1 or something like that. If any of these 4 conditions is violated, then we're going to say, oh, not only are we not going to push that into the array for threatened, not only are we not going to push it into the array, we're also just going to break the loop right then and there and not repeat it at all. Not a single more iteration after this. But that's just for this loop. Keep that in mind. It'll still move on to the next iteration of this outer loop. So it'll go as far as it can in one direction, and as soon as it can't go any further, it's like, oh, okay, try a different direction then. And it could be that, like if you do have one starting in the corner, it would only be able to go in this one direction. It would just stop the loop, stop the loop, stop the loop, and only do this one. Okay, so that's basically what's going on. The only thing we haven't talked about is this line right here, which is basically if it is in range, if we're going steps further and we find that it is in range, then we're just going to do threaten.push, but specifically with get position of tempx and temp_y. Now, why am I doing the get position thing here? Like, why bother having them in these chess codes? Why not just actually, put them in like a little array or something like that? Keep them as coordinates. That's what we've been working with. We like coordinates, right? What could be wrong with something like this? Well, here's the issue. What I'm trying to check is to see if threatened actually includes the coordinates of the pawn. So if I keep it the way we had it here, where it's doing get position, well, now it's already in the form that we're looking for. So in this case, we're expecting a false. Let me get a true one. So in this case, it's true because C3, the position of the pawn, is within our threatened tiles. So really, all we need to do is, threaten.includes pawn. That's really what we're trying to check here. Look at that. It's passing all the sample tests. Okay, so that's cool. But I do want to say, even if we did it this way, so even if we made it something like this, where, and actually I'll do a little console log of threatened in here just to see what we're getting. So now, this obviously isn't going to work because pawn is not in the right format. Pawn is in a chess notation, whereas all of these are in coordinates. So it's saying, oh, okay, well, why don't you just do a get coords on that? And that way it will give you the actual array of coordinates that pawn is. So we look at this and we think, okay, well, that's strange because pawn, it says C3, right? So C3, that's like the coordinates would be 2, 2. And we can see 2, 2. It's right there. So why is it saying that it's not? Well, the thing is, these are arrays, right? So we have to keep in mind this whole business about pointers and addresses. And the idea is that you can have an array that contains the elements 2 and 2, but that doesn't mean it's the same as every array that contains those same elements. They're different arrays. They point to different things in memory. They just happen to contain the same elements. So I can't easily make a comparison. I can't easily check my dot includes with coordinates with an array. So that's why I need to just, or I shouldn't say I need to use my, get position. Yeah, get position of tempx and temp_y. The reason I do that is basically to make it much, much easier to do this dot includes business. But there are other ways to do that. There are other ways. In fact, we can, we could talk about another way of doing this. That might be fun. So let's try submitting this first. Let's see if this passes. Ooh, yeah. We're passing the hidden tests, and you know what? We just cleared the dank wilderness, so that's nice. Extra 5,000 coins definitely doesn't hurt. And look at this, we're 70% of the way through. Now that's really exciting. I hope you're as excited as I am about that. You probably are. Anyway, okay, so we'll close that for now. And what were we gonna do? Well, first of all, I think this is great. I think it's really neat. I like this algorithm. I'm a big fan of it, actually. But, if you love something, you gotta let it go. So I'm gonna wrap that up for now. And we're basically just going to copy it because we're going to chisel away at it and see if we can create something even more beautiful. Or at least something different. We'll see. So, do I use get position in any other spot than here? No. I don't. Yeah, I don't. Okay, so instead of get position, we're going to do something a little bit different. We're going to say get hash. Okay, so basically the way this is going to work is we're just going to say return, we'll say, okay, hold on a sec. how are we going to do this? We could do something that's like 10 times x plus y. One semicolon's probably enough. Yeah, 10 times x plus y. So what am I doing with that? Well, basically, I'm taking our coordinates, x and y, so maybe the coordinates are like 2, 3, let's say, right? So if it's 2, 3, and I want to represent that as a number. I'm calling it a hash here. This is a very basic example, but the idea is I'm trying to represent some kind of string or some other information, a string, an array, you know, something that's like multiple things, and I'm trying to represent it as a single number just for ease of comparison, for memory management, that kind of stuff. So basically, if I do 10 times x plus y, what I'm thinking is that that's going to give me a unique number, because basically if okay, let's think about it this way. Let's go up a column. So x is 0, y is 0, x is 0, y is 1, x is 0, y is 2. So if we did this 10 times x plus y, we get 0, 1, 2, 3, 4, 5, 6, 7. And then from here, since x is 1, we get 10 times 1. So we get plus y. So we get 10, 11, 12, 13, 14, 15, 16, 17. Then we get 20, 21, 22, 23, 24, 25, 26. So basically the idea is that every one of these squares is going to get converted to a unique number. We're never going to have the same number from two different squares. So that's nice because we're equally representing these things. But it's also nice because now it's just a number. It's not a string that we have to compare. It's just a number. So instead of get pause, I'll say get hash. And yeah, it's just giving us a hash code. Well, really, I mean, it's just giving us a number. Normally, we wouldn't just use 10 and 1 here. Like, normally we would multiply these by large primes, maybe do some modulus stuff on them. Maybe we'd have a hash table, a hash map, or something like that. And, you know, those are concepts that that we'll get into for sure. Okay, I did record a video about this, but I haven't posted it yet, and we'll talk about that after. The main thing is, for now, so we get hash, and now let's run this. Let's see what we're getting, mainly from the console log. That's the part I'm interested in now. So check it out, 11, 22, 33, etc. It's kind of like we're getting the coordinates, but instead of like 1, 1, it's just 11. It's just the two digits pressed together, because we know that these codes are the coordinates are going to be one-digit numbers anyway. They only go from 0 to 7. So that's why we don't need to worry about like multiplying by large primes and stuff like that. Okay, I mentioned a few examples of advantages we get from using hash, like, you know, making it go faster, making it easier to compare these things, but also it might be for security or like encryption or something like that, and that's where you'd want to put the large primes or something like that in. But anyway, the point is I'm not too worried about that for this example. It's just I want to make this easier to compare. That's the main thing. So the problem is we're still saying, does it include pawn? Really what we should be saying is get hash of pawn. But oh, wait a sec, get hash accepts two variables, x and y. So it's like, what are you even talking about here? What it should be doing is get hash of get coords of pawn. And then even that is going to have a problem, because get coords gives us an array with two elements, not just the two elements. So we actually need to spread this out and basically say, well, we don't want to give get hash the array as a single argument. We want to give get hash two arguments, which are the contents of that array. So we'll run this one, and now we find, yeah, it passes all the sample tests. Now, we did have to run kind of like, you know, some additional functions down here. I would say ultimately, in terms of like comparing these two, probably this bottom one is better for clarity. Like this final line, I have to say, I love this line of code right here. And the reason I love it is because it is so absolutely clear what it's saying. Return threatened includes pawn. That's it. Is the pawn being threatened? Is it in the list of tiles that are being threatened by the bishop? That is such a self-explanatory thing. Like, I don't need to even leave a comment on that, because anyone else looking at this code can basically read this like a sentence. So that, to me, that's beautiful. That is an element of programming not to be overlooked, the human readability, the clarity element of it. Okay, so this one not quite as clear. Not quite as clear for a few reasons. I mean, number one, this stuff here is a lot more complicated than just pawn. So on one hand, there's more words to read here and it's a little less clear, but also like there's so much nested stuff here that the reader might get discouraged. You know, it might be overwhelming to look at all this stuff. Anyway, I don't want to go into too deep a tangent on human readability, but the main thing is that I would say this one is more human readable. This one, if I had to take a guess, I'd say is probably faster because I think it's easier to compare two numbers than it is to compare two strings. But to be honest, I wouldn't be able to tell you that for sure. Like, you know, you need someone with more knowledge than me. Okay, so, all right. Oh, by the way, if you know, let me know. Leave a note in chat, leave a comment or something like that. Yeah, don't leave me hanging. Anyway, the point is, this worked, right? I think we were able to submit this one. It was just good. Yeah, I think probably that one's a bit faster than the other one, but it's probably like marginally. Anyway, not to worry. We're gonna let that one go too, and we're gonna do a new one here, and we'll use part of this stuff over here. So let's pop that in. So, okay, here's where things get really fun, actually. So this is gonna be kind of cool. I actually want to do something that's, I think kind of neat. So I'm going to say const, and I'm going to find the coordinates of our bishop and the coordinates of our pawn. So we'll say x bishop, y bishop. And it's going to just be get coords of bishop. Notice I'm using a destructuring argument here, so I'm assigning the values of x bishop and y bishop, but I'm doing them together. They're not actually going to be in an array together. This is just a way of just easily, more efficiently declaring them, so that I don't have to say like, let coords be assigned the value of get coords bishop, and then let x bishop be assigned the value of coords at 0, and let y bishop be assigned the value of get coords at 1. This is just a lot more efficient than that. And then I can say something like const x pawn, y pawn is assigned the value of get coordinates of pawn. Yeah, you can do something like that. In fact, I think we could probably make this even more efficient by just doing something like this. Yeah. No sense in repeating ourselves with the word constant there if we don't have to. I could have done something similar up here, I guess, but anyway. As you've probably noticed, I'm not usually afraid of a little repetition. Okay, so here we go. We've got our positions here. We've got our coordinates. Why am I so interested in those? Well, it's because I noticed something. I've been looking at these, and I've been looking at the situations where we are going to be able to take the pawn and where we're not going to be able to take the pawn. And I've noticed kind of a surprising pattern. So let's get a little pawn in here. What does a pawn look like? Like that, I guess? Yeah, kind of like that. Okay, so if the pawn's here, can the bishop take it? Oh, yeah, it can. It's right in the threatened range there. So let's take a look. Let's do a little analysis here. Let's have a look at its position here. Well, if we look at the x difference, that's 2 tiles. And if we look at the y difference, also 2 tiles. Okay, so maybe that's a coincidence. We'll find out. Let's take another look at one that would be threatened, and then maybe after that we'll look at one that would not be threatened. So let's say this one down here. Wow, these pawns are I guess I'll just say I wouldn't want to play with this chess set. Okay, so this over here, these have an x distance of 3 and they have a y distance of also 3. So okay, the hypothesis is getting a little stronger here. Let's switch colors and we'll look at this case where they're not gonna where it should fail, right? So this distance would be 3 in this case, and then the x distance would be 1. They're not the same. So it seems to me like if the difference in their x values is the same as the difference in their y values, then it should be true. The bishop can take it in that case. If they're not the same, then the bishop can't take it. It would just fly right past. So we don't need to worry about doing all these threatened squares and stuff like that. Really, all we need to do is say the absolute difference between the x bishop position and the x pawn position is the same as the absolute value of the y differences, the difference between the y position of the bishop and the y position of the pawn. And if they are equal, boom, we got it. One more thing, I just want to put in a triple equal because, you know, I want to get in the habit of that. I think it's generally better. So again, the difference between that is we're not just saying that like these two things would get typecast to the same value. We're saying they are the same value. So like, for example, if this one was like the string 0 and this was the number 0, well, these would not be equal. Whereas if we did it with 2 equals, then yeah, they would be equal. Anyway, point is we're going to leave it like that. And is this going to work? Is this going to pass all the hidden tests? Oh my God, look at that. So that saves us a lot of effort, I think, right? I mean, that's like, when you think of all this threatened stuff we were doing, like we had an array of arrays just to tell us like what direction to go in for our loop within another loop. So like this, it got a little heavy, you know? We're really economizing a lot by just doing this stuff. And something else to notice, we didn't actually have to convert back to position. We didn't need this function anymore because it's taken care of. I mean, like, we're making the comparison without looking at their without looking at anything other than their coordinates, and in particular the difference between their coordinates. So cool. I feel good about that one. I think this one is going to be, well, okay, yeah. So we could talk about time complexity here. I don't think it's going to be super easy because like the number of squares that the bishop's going to be threatening is really like, you know, I don't think there's like a one-to-one like relationship between the position on the board and like how many squares is going to be threatened. Like, okay, the minimum number would be 7, the maximum number would be 14, I guess. No, not even. You could, yeah, this would be the maximum number because you get 7 from this, 6 from this, so 13. 13 is the maximum number. So anywhere between 7 and 13 squares, I guess. That's kind of, yeah, I don't know. Anyway, the point is, time complexity, I think they're probably like pretty similar. The thing is that like this problem isn't going to get that complex. You know, there's not that much to do. Like at most, threatened is going to have a length of, what do you say, 13? It's just loading it up can take some time, but even, you know, not that much. It's just a lot of writing, a lot of code, a lot to understand here. It's not that difficult to actually execute it though. It's actually not much more difficult than this. Now, if we were talking about like an arbitrarily large chessboard, and the chessboard could be more than just like an 8x8 square, then yeah, it definitely, like these ones down here would be a lot more complex. Time complexity would be a lot greater on these if one of the variables was the size of the board. Whereas this one would be totally fine. You know, like the size of the board makes no difference in terms of how this algorithm is going to run. So I was about to make a comment, you know, something like, doesn't depend on the size of the board. But then I realized, like, if someone's reading that without seeing the video, they'd be like, what do you mean it doesn't depend on this? Of course it wouldn't depend on the size of the board. The size of the board's a constant, you idiot. So, yeah, okay, maybe I won't make that comment. Okay, great. So glad we finished that one. Nice job, everyone. Let me know if you have any questions, comments, or concerns. Put them in the chat, put them in the comments. And yeah, great job. We're done. Okay, so I think that's going to be the end of the stream for today.